This lesson is on 4.3 Logarithmic Functions. Here are the things you need to be able to do after this lesson. Let's consider the following. If I gave you 2 to the x equals 8, would you be able to solve this? What does x equal? Okay, 2 to the what power gives you 8. The correct answer is 3, right? Because 2 cubed gives you 8. Right? Okay, straightforward enough. What about this one? What if I told you that 2 to the x is equal to 5? 2 multiplied by itself, how many times would give you 5? Okay, can you find the exact value? We know that 2 squared, right, gives you 4, and 2 cubed gives you 8, so x must be a number between 2 and 3, but we need the exact value. So how can I get this x by itself? Right now it's in the exponent, but I want it down here, right? How can I undo that? So you can undo that by taking the log of each side. So you take the log of both sides. That's actually an operation that you can do. And we're going to take the log of this same base 2. See how it's base 2 right here? We take the log base 2 on these, and that operation actually undoes it. So you get x equals log base 2 of 5 as your exact value. So recall from last class that the inverse of an exponential function is a logarithmic function. So I can undo that exponential function by taking the log of both sides with the same base. So just as you can take the log of both sides of an equation, you're also able to do something called exponentiation. So you can exponentiate both sides of an equation. Here's what I mean. Remember the x equals 3? Let's say we have x equals 3. If I want to make those into the exponents, I can exponentiate both sides by the same base. So I can exponentiate both of these by base 2 if I want to. So now I've made my equation 2 to the x equals 2 cubed, which is 2 to the x equals 8. Right, notice that's the original problem that I had. So 2 new operations that you've learned is exponentiating both sides by the same base and taking the log of both sides by the same base. So remember we got for number 2 that x is equal to log base 2 of 5. Log base 2 of 5. How would you put this into your calculator? Try pressing math, alpha, math on the upper left-hand corner. So math, then alpha, then math. And if you get this on your screen, then that means you have a updated version in your calculator and you can just use that. So math, alpha, math. If you get this, then you plug in 2 and 5, giving you 2.3219. If you hit math, alpha, math and nothing happens, that means you're going to have to go using a formula way. So then you would have to hit log of 5 over log of 2. So the log button is in the left column down towards the bottom. And if you hit that, that will give you the same answer of log base 2 of 5, which is 2.3219. Okay, so the formula, if you do not have an updated version of the calculator, is the following. Log base b of a is equal to the log of a over the log of b. Go ahead and try this problem. Evaluate log base 3 of 10, rounding to 3 decimal places. The correct answer is 2.096. If you don't have the updated version of a calculator, again, you would have had to type in log of 10 divided by log of 3. Just like multiplying and dividing by the same number would undo each other, exponentiating and taking the log of both sides by the same base would also undo each other. So these are inverse operations. Here's another way to think about logarithms. Let's say I had base b raised to the power of x equaling a. I could rewrite this in a different form. So the way I can rewrite this in a different form, but with the same meaning, is as follows. It's going to be the log base b of a equals x. So the log base b of a equals x. If I want to go backwards into the exponent form, it will be b to the x is equal to a. Notice both the bases are the same. It's base b. What's different is that the exponent, right, the exponent here is the answer to the logarithm. So a logarithm can be thought of as follows. It's the exponent to which a specific base is raised to obtain a value. So the exponent is the logarithm, or the answer to a logarithm, right? The x is the exponent. Let's take a look at an example. Rewrite in logarithmic form. You have 3 squared equals 9. So log base 3, because the base stays the same, of 9 is equal to 2. So log base 3 of 9 is equal to 2. Remember, the answer to a logarithm is the exponent. Here's another way to think about this. You can take the log of each side, remember that's an operation you can do, and take the log base 3 of each side. And I do that because then the log and the exponent will cancel out, giving you 2 is equal to log base 3 of 9. Notice that we get the same exact expression here. Log base 3 of 9 is equal to 2. More on this later when we solve equations. Okay, go ahead and try this problem here. Here's the correct answer. Log base 5 of 1 is equal to 0. Log base 5 of 1 is 0. Again, the exponent is the answer to the log, and then the base is the same here. The second way to think about it is to take the log of each side, and I want to get rid of this base 5, bringing down the exponent. So I take the base 5 of both sides. Log base 5 of both sides. These cancel, giving me 0 is equal to log base 5 of 1. Okay, let's try going the other way around. Write in exponential form. You have log base 5 of 25 is equal to 2. So again, 5 squared is equal to 25. The base stays the same. 5 squared, remember the answer to a log is an exponent, so 5 squared gives you 25. I could also think about undoing the logarithm. So if I want to undo the logarithm, I can exponentiate both sides by base 5. And I chose base 5 and not some other number because I see that log has base 5. So I have to make them match. When I do that, these cancel out, giving me 25 is equal to 5 squared. Go ahead and try this problem. Rewrite in exponential form. So the correct answer is 2 to the 4th equals 16. 2 ways to think about this. 2 to the 4th equals 16. Or if you exponentiate both sides, these cancel out and you get 2 to the 4th equals 16. Okay, here are 2 special logarithms. The first one is when you have a base 10. Okay, so a base 10, that is also known as the common logarithm, or common log. And the second one is when you have base e. E is a number that's about 2.7. We'll talk more about that in the future. And this is known as the natural logarithm, or natural log. So these are special because you'll see that on your calculator, you'll have natural log and common log as its own button. And this is how it looks. Common log is going to look like log of x. Natural log will look like ln of x. Okay, common log, log of x, that's really log base 10. But that 10 will be invisible, so this is how you'll see it denoted. ln of x is really just log base e of x, log of 2.7-ish of x. But the way that log base e will be denoted is ln of x. So here are some properties of exponents that I want you to remember from last semester. 3 to the 0 is 1, right? 4 to the negative 1, that negative exponent makes it a reciprocal. It makes the base a reciprocal. 4 to the negative 2, that's 4 squared, but flipped over, right? When you have fractional exponents, then remember the bottom number is going to tell you the root. Remember, the root of a tree goes down. The bottom number tells you the root or the index of the radical. So 9 to the 1/2 is just square root of 9. If I have 9 to the negative 1/2, I take the square root of 9 and I raise it to the power of negative 1. So it's 3 to the negative 1, giving me 1/3. Okay, let's take a look at some example problems. Evaluate. Remember, that means just to find the value. What is log base 3 of 1? So you're asking yourself, 3 to the what power equals 1, right? 3 to the what equals 1? The answer is 0. What about here? 5 to the what power equals 1 over 5. 5 to the what power equals 1 over 5? That's negative 1, right? 5 to the negative 1 is 1/5. How about with this logarithm? What is that invisible base? It's base 10. This is a common log. 10 to the what power gives you 1,000. Okay, it's not 100, it's 3, right? 10 cubed gives you 1,000. Okay, the last two are a little trickier. 25 to the what power gives you 5. 25 to the what power gives you 5. Okay, when you take the square root of 25, you get 5. And the way you denote square root as an exponent is 1/2. So that 1/2 is your answer. 25 to the 1/2 power gives you 5. Okay, let's take a look at this last one here. 9 to the what power gives you 1/3. So when I see this, I think square root of 9 gives me 3. So I think 1/2, because square root of 9 gives me 3. But see that it's the reciprocal. So how could I get it to be reciprocal? The exponent needs to be negative. So the answer is negative 1/2. So you try this problem. What is log base 3 of 81? So the way to do this is to think 3 to the what power gives you 81. 3 to the what power gives you 81. Well, 81, right, is 9 times 9, 3 times 3 times 3 times 3. So notice that you're multiplying 3 by itself 4 times. So 3 to the 4 gives you 81, therefore the logarithm is equal to 4. Remember, the logarithm is the exponent, right? So log base 3 of 81 equals 4. Go ahead and try this one. What is log base 8 of 2? Right. 8 to the what power gives you 2. 8 to the what power gives you 2. Notice that it got smaller, right? Got smaller. I had to actually take the cube root of 8 to get out 2, right? 8 is 4 times 2, 2 times 2. Notice that the cube root of 8 is equal to 2. Therefore, to rewrite cube root in rational exponent form, that would be 1/3. So 8 to the 1/3 equals 2, right? Because cube root of 8 equals 2. Therefore, 1/3 is the correct final answer. Okay, go ahead and try this problem here. Right. Remember, if you don't see any base there, that is going to be the common log of base 10. 10 to the what power gives you 0.01. Using the hint where 0.01 in fractional form is 1 over 100, I'm asking 10 to the what power equals 1 over 100. So when I see this, I see that 10 squared would give me 100, but I need the reciprocal. So if I want to make it the reciprocal, I need a negative exponent. Therefore, negative 2 is your final answer. 10 to the negative 2 gives you 1 over 100, which is 0.01. Okay, and we're asking ourselves 100 to the what power gives you 1/10. So 100 to what power gives you 1 over 10. So I see that it's fractional, so it's probably going to be a negative exponent because it flips it. But notice we went from 100 to 10. So square root of 100 is 10, right? Therefore, 100 to the 1/2 gives you 10. So we know we have like a half, but because it's flipped over, it's not 10, it's 1/10. We have to make it negative. So again, 100 to the negative 1/2 power gives you 1 over 10 because that's square root of 100, which is 10, and I still have that negative 1. 10 to the negative 1 is 1 over 10. Final answer, negative 1/2. For this problem here, you have to use your calculator. The correct answer is 3.700 if rounding to the nearest thousands or 3 decimal places. If you don't have the updated version of the calculator where math alpha math doesn't work, you would have to use a formula. So in this case, you would do log of 13 over log of 2 and you get the same exact answer. An easy way to remember this is to just think the smaller number or the bottom number goes on the denominator, right? And the bigger number, like the 13, goes in the numerator. But you have to write log twice. Let's take a look at an application example. Acidity is measured in pH as given by the following function. So the pH is blah, 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 where this, right, represents the hydrogen ion concentration. So this is concentration of hydrogen ions in moles per liter. Question asks you, find the pH of tomato juice with the hydrogen ion concentration of 0.0000316 moles per liter, rounding to the nearest tenth. So go ahead and try this. Could you do this problem using your calculator? Okay. This formula, if it were on a test, it would be provided to you. So to find the pH, all you would do is do negative, hit the common log button, and inside put in the moles per liter, right? That's the concentration of hydrogen ions in this particular solution. Plug that into your calculator. Rounding to the nearest tenth, we get 4.5. So the tomato juice has about 4.5 for its pH level.